Okay, so I will discuss in my lecture a topic which is somehow connected to the previous talk and also to a seminar we had last week, which is to analyze three-dimensional gravity on spaces with multiple boundaries. And the reason why it's of interest is that that gives you a very tractable example where you can work out all the formulas to the end of a gravitational model that does not factorize into independent theories living on the boundary. So as we know, ADS gravity has no bulk degree of freedom, so we can reformulate it as a entirely as a theory living on the boundary. And whether the multiple boundaries bound a connected region or a disconnected region can be seen in the resulting theory living on the boundaries. So, as we will see, in one case we get additional, well, in the case of the black hole, as that I will discuss, we get additional holonomies and Wilson lines that connect the two boundaries, something that would not be the case if we had a theory on independent, on two disks. Well, I will explain. Okay, so that is related to something we heard last week, and as I said, I want to be rather explicit in this talk, and I will consider the case with two boundaries, although in principle we could consider situations with more boundaries, but the ideas are just the same. So as I said, it's a direct line of the course, and I will try to be relatively pedestrian. Maybe I will not derive all the formulas, but I will try to be explicit about all the steps. And it's connected with the seminar given last week by Jonah Edmanger. Okay, so I will I will continue the introduction by giving some references. Then I will recall what is the eternal BTZ black hole, in particular the topology and the holonomies. Then I will discuss very explicitly, because that's simple and in a sense the ideas are the same, the U1 Chern-Simons theory on an annulus, which has two boundaries. I discuss the theory on a disk in the lectures. There is only one boundary in that case, so that we will be able to compare rather easily what are the differences. Then I will extend to ADS3, and then I will conclude. Okay, so it's based on the following two papers, but it finds its roots in many more references, and I will only mention three here, but the list is far from being exhaustive. One is a paper by Monica Guica and Daniel Jefferies, which pointed out the importance of Wilson lines connecting the boundaries and how they enter in an important and crucial way in the discussion. Then there is this paper which tried to understand the implication of that puzzle. And then there is a paper about which we heard last week. Okay, so let me start with the BTZ black hole. So I've shown in my previous lectures that three-dimensional gravity with a negative cosmological constant admits black hole solution. And if I draw the Penrose diagram for the non-spinning case, for simplicity, this is what we get. And there are two asymptotic regions, which are here denoted sigma 1 and sigma 2, which are connected by, well, here it's a line, but if you look at what this line is, each point is a circle, so this is really a cylinder. So you get something like that. So you have a wormhole connected to asymptotic anti-de Sitter regions, one here, well, and this is time. And this cylinder is the same as a disk. And so we would have one, well, I will call the outside boundary, but it's, they are completely equivalent, of course, so it's a terminology. So I would have one boundary here and the other boundary here, and this is the interior. So this is a fixed time slice, and as I said, it's a wormhole. Now, The gauge group for, so we have also seen that anti-de Sitter gravity in 3 dimensions is equivalent to a Chern-Simons theory with gauge group SL2R cross SL2R. Now there are different types of holonomies for SL2R, so let me just focus on one copy. So for the black hole, the holonomy is hyperbolic, and I will say in a second what that means. But so in particular, that means it can be conjugated to a diagonal element, so some number, real number, times the Cartan subalgebra element L0, which I introduced last time, and I will rewrite the matrices in a second. So I drew explicitly the Penrose diagram for J angular momentum equal to 0, but the same can be developed in the general case. Now, just for definiteness, the basis of SL2 generators which I take is this one. So L0 is Cartan subalgebra, and then you have the raising operators and the lowering operator, and for some reason that I do not completely remember, we took the following conventions for normalizing the matrices, and that gives these commutation relations, and these you can compute the trace also. So the Killing form. Now this invariant metric it's a non-compact algebra. It has signature minus plus plus. Okay, and so if you look at an element in the Lie algebra, you say that it's hyperbolic, parabolic, or elliptic, depending on whether its norm squared is strictly positive, 0, or negative. And a typical hyperbolic element is L0, and in fact any hyperbolic element in the Lie algebra can be conjugated to a multiple of L0. So for the which actually is the case for the black hole case. Now for a parabolic element can be seen as a multiple of L plus, and the multiple has no particular significance. You can even absorb it. So that's, as you can see, L plus is here. So that's typical parabolic element. And then the compact subalgebra would be, generated by L minus as L plus. So this generates SO2, the SO2 subgroup, and an elliptic element would be can be conjugate to such, to a multiple of L minus minus L plus. So as I said, for the black hole, and I wrote asymptotically after a global gauge transformation, one can write the connection at infinity like this, and you can compute the eigenvalues of this matrix. They are real, and plus or minus square root of m over 2. It's a simple exercise, just diagonalize the matrix, and then you will find that it's conjugate when you diagonalize it to a multiple of L0, with the multiple being square root of m. So there is a 1/2 in L0 in the way I defined L0. Now actually the holonomy is really what you would get by integrating this, so the path-ordered exponential of the connection around the circle. This is what you really call the holonomy, but because this does not depend on phi, there is no path ordering to worry about, and the matrix is commute at different value of phi. It does not depend on phi, so the exponential is very easy to compute. So if you use that, you will find that it's 2 pi times this. So the holonomy is really that matrix, but I will call the holonomy K0 for. It's an abuse of language, but this is what I will mean in later. Okay, so now if you compute the holonomy for ADS3, you find that it is elliptic, and you find in fact the value -1, which might be surprising because you would expect no holonomy, but that's because the fact that you find -1 is because we are working with SL2R, the SL2R representation of SO21, and in polar coordinates, and as you go around the circle, the polar frame will make a 2 pi rotations with respect to the Cartesian frames in which things are continuous, and you pick up a minus sign as you do that. So this is not a surprise, that was expected, and this is what you get. There is nothing wrong with that. It doesn't mean that it's not contractible, it's just that the polar coordinate system is singular at the origin. For conical singularities, you can also compute the holonomy, and you will find that in that case the holonomy is elliptic. I mean, as you go around, you generate a rotation, and so it's not a black, well, it's different from the black hole. So the distinguishing mark of a black hole is that the holonomy around the black hole is hyperbolic. Okay, and so can be assumed to take that form. Okay, now let's try to rewrite three-dimensional gravity on an annulus in terms of boundary theory. Since there is no bulk degree of freedom, we can explicitly solve the constraints and eliminate the field and express everything in terms of boundary data, or we can try to do it at least, and let's see how it goes. And because ADS gravity is a Chern-Simons theory, I will first review, actually something that we did in a previous lecture. I will review how it works with a simplest Chern-Simons theory, the U1 Chern-Simons theory on a disk. So let me recall how we can reformulate that three-dimensional theory as a two-dimensional theory living on the boundary. Now, as we saw, well, actually we worked that out. We solved explicitly the constraint, and we saw that the observables of the theory, the gauge-invariant quantities, were the values of the angular component of the vector potential at the boundary, which fulfill a Kac-Moody algebra, U1 Kac-Moody algebras. And so they are called also Kac-Moody currents for that reason. But they were not completely independent, because as you go around the circle, this is a contractible circle if you are on a disk, the integral of a phi around the circle should be equal to 0. So the zero mode of J, if you want the potential to be continuous everywhere, should be 0. Then we computed the brackets of the currents. These are the asymptotic charges of the asymptotic symmetries. And we found that indeed that was a Kac-Moody algebra based on U1 with a central charge that was related to that K, as follows. Now, it was the way we arrived at these currents that we were looking for the observables. That means that we were looking for the quantities in the Chern-Simons theory that was gauge invariant under the proper gauge transformations, those that correspond to a true redundancy, that do not change the physical state of the system, and these are just, in that case, the gauge transformations that vanish at the boundary. And of course, if you make a gauge transformation that vanish at the boundary, A phi is invariant. It transforms as a gradient of the gauge parameter with respect to, the derivative with respect to phi of the gauge parameter at the boundary, but if you take a tangential derivative of something that vanish, it's 0. Okay, now what is perhaps important to realize is that and I think I also mentioned that if you give me the current at the boundary, you in fact know completely the system, in the sense that you can completely reconstruct the gauge, the potential, Phi and AR, within the disk up to a proper gauge transformation. And since proper gauge transformations are just redundancies, you have all the physical information you need. So from that point of view, the currents, restricted by this no holonomy condition, form a complete set of observables. Now, I also mentioned that in order to define the dynamics at the boundary, you have to tell how you choose the temporal component of the connection, and it's in relation with ADS, it's a useful condition to impose. So I take AT equal to A phi, and in that case, the boundary Hamiltonian that we worked out was just the square of the current integrated over phi. Okay, so that's the one boundary theory. We can actually reformulate it in terms of dynamical degrees of freedom at the boundary. That's the chiral boson reformulation. So you solve, the idea is that you solve the zero curvature condition on the disk. Then on the disk, if the curvature is zero, AI can be written as a gradient where mu is globally defined. But of course there is in this writing some redundancy, because if I shift mu by something that does not depend on the spatial coordinates, so by something that depends only on time, it drops. So many mu's define the same AI, but it's important to realize that mu is well defined. So I can re-express the theory in terms of mu, and this will appear as a gauge invariance. So if I do that, if I reinsert that expression for AI in the Chern-Simons action, I can integrate over R, so I will get a pure two-dimensional actions where depending on t and phi, so a boundary action. And the boundary action is just actually what people call the action for a chiral boson, where the boson in question would be the value of the gauge parameter at the boundary, which I have called R1. So this will be the value of mu. So if you get this action by inserting that expression into the Chern-Simons action, integrating by part. Well, be careful with boundary terms because that's the Hamiltonian, and this is what you get. And this is a chiral boson because it leads to the equations of motion, as you can see by varying with respect to phi, that phi dot minus phi prime is equal to 0, so phi dot minus phi prime is equal to a function of time, but that's precisely the gauge invariance of the system. So that's, of course, if you don't fix the gauge, it's normal that you get that. You can see directly on this form of the action that indeed the redundancy that I mentioned appears as a gauge symmetry. So if I shift phi by something that depends only on time, I will get something that can be integrated, that will depend only on time, so it does not depend on phi, goes out of the integral, and then I get the zero mode. I get something which integrates to 0, and here, well, phi prime is invariant under that, so that's clearly invariant. So indeed, we get this gauge symmetry. Now, so that's something that, in a sense, was covered already previously. So now the interesting thing is to compare that with what we would get on an annulus. Now, in that case, the holonomy doesn't need to vanish because the boundaries are not contractible, so you could get some non-vanishing value for the holonomy, but of course it has to be the same since the curvature is equal to 0 at the two boundaries. Now, if you crank the machine, compute the asymptotic symmetries, look and only quotient by the ones that are proper gauge symmetry, so that have 0 charge, you in the end get something that first looks like two copies of what we found for a single boundary. Namely, you find two commuting U1 Kac-Moody algebras, so which would be the value of the vector potential at the two boundaries. So the first I call J, the other M. And, well, but it's not, there is already something which is not quite the same as in, it's not just the product of, two copies of what we found previously, because here the holonomy need not be 0. But of course, both, if you compute it with J or with M, which are the value of the vector potential at the respective boundaries, you should get the same thing. But K0 now is a degree of freedom. It need not be equal to 0. So this is just what I said. And at the same time, you can see that the Kac-Moody currents, even subject to the holonomy conditions that I wrote, do not form a complete set of observables anymore. They are additional quantities which are invariant under proper gauge transformation, so under gauge symmetries that vanish at the boundary, because that's the only ones by which we can factor out. But they cannot be expressed in terms of the boundary field. So they are extra degrees of freedom, and this is and it can be identified easily as a radial Wilson line. So the integral of the vector potential along a line that joins the two boundaries. So this is a radial Wilson line that appeared, I think, in that context first in the paper by Monica and Daniel that I mentioned at the beginning. But here it appears also. And it's clear that it's gauge invariant under proper gauge transformation. Well, it might only transform, it will only transform, as we know, under gauge transformations at the boundary. But at the boundary, proper gauge transformations vanish, so this will be invariant. And it's clear that it cannot be expressed in terms of the boundary field. It contains more information. And so there is one new global degree of freedom, this radial Wilson line. Now you might say, well, maybe there are many more, because actually I can go from one boundary to the other boundary through different lines. But you can show that if you take a different line joining R1 to R2, it will differ from this Wilson line by terms that involve the integral of the vector potential along the boundaries, if you choose different endpoints. But these can be expressed in terms of J and M. So there is only one new global degree of freedom. Any other Wilson line can be expressed in terms of that one, and in terms of the Kac-Moody currents, which are already part of the system. And now, from the point of view of the dynamics, you can show that this additional global degree of freedom is in fact canonically conjugate to the holonomy, in the sense that they have Poisson brackets equal to 1. Well, that's easy to identify here because it's the abelian Chern-Simons theory. One way to do that is just to, again, re-express the dynamics in terms of the physical fields. So in that case, we will introduce again a parametrization of the vector potential in the bulk in terms of mu, of a field mu, which is, it can be by solving the zero curvature condition. And this is what but of course the zero curvature condition involves also the holonomy if you want mu to be well-defined field periodic in phi. And then if you substitute, make the transformations, this is really a direct computation, so I'm not going to give the details, but what you get is, well, what you somehow expect now, is that you will get two boundary actions, one involving the chiral boson at one boundary, and the other, which I call phi, and the other involving the chiral boson at the other boundary, which I call psi. So this is the value of this parameter, but one at R2, the other at R1, the other boundary. And well, so this is the action, so this is very similar to what we found for a single boundary theory. And then on top of that, we have a piece that comes from this term in the vector potential, and that involves the difference, the time derivative of the difference between phi and psi integrated over phi. So K0 does not depend on phi, so I could have written it here. Well, just the reason why I get a minus sign here, well, they are, first of all, it's the other boundary, and then also I have imposed that condition at the inner boundary to get a positive definite Hamiltonian there. But that, I mean, there are many other boundary conditions we could envision. But then we have also a Hamiltonian for the holonomy with these choices. Okay, but so let's focus on the degrees of freedom.
Sorry.
Yes?
Just one question. Regarding the Hamiltonian, there's nothing that forces the two Hamiltonians to be the same. You could choose one. I mean, you could choose different behaviors for A0 on the two different.
Yeah, I could have different profile for phi and psi. Yeah, so the derivatives might not be equal. So
exactly. Okay.
Phi could be 0 and psi not 0, for instance.
Sure. So it's a choice in a sense you make. It's like
No, but this is the dynamics. This will depend on the initial conditions that you impose. Yeah. Mm-hmm. But even though the value will depend on the specific solutions, the form of the Hamiltonian is the same because it results from the same integration by it results from the same integration by parts evaluated at the two different boundaries. But you might say it's a choice of parametrization also. But for definite solutions, it will take different values. Now, this action has a gauge symmetry. You can shift, just like for a one-boundary theory, you can shift by a time-dependent function. So this comes from the parameterization. If I shift mu by something that depends only on time, clearly this is 0, and that's a gauge symmetry. So this action is invariant, this action is invariant. But you see that you have to take, in order for that to be invariant, the same shifts for phi and psi. Otherwise, the action would not be invariant. But that's normal because it corresponds to the shift of that single function mu. So that's gauge invariant. And so that corresponds to a redundancy in the description of the theory. And we see that also the conjugate to the holonomy is the integral over phi, so the zero mode of the difference between phi and psi, between the two chiral bosons at the upper boundary and the lower boundaries. Okay, now the action itself, as we have seen, involves the sum of two boundary actions, each describing a chiral boson, as in the one boundary theory. But there is this zero mode, which involves the holonomy, which is common to both boundaries. So it does not really belong to one boundary, it's the same at both. And the zero mode of the gauge invariant expression, which is conjugate to K0, and which we can identify as a radial Wilson line, as I will show now. So we have that AR is dr of mu, because, and so if you integrate that expression, given the definition of mu and phi and psi, you will just find the difference. So indeed, you find that this is the radial Wilson line. As I said, it's manifestly gauge invariant under all proper gauge transformations. Now, as I said, well, I say the holonomy because there is only one. You get always the same value no matter which value of r you are evaluating the holonomy. And the radial Wilson line, no matter how you integrate from one boundary to the other, you will get a Wilson line which is a function of the given one plus the other degree of freedom. So there is only one independent radial Wilson line. And they are canonically conjugate in the abelian theory, as we can see from the action, which is here. This we read from here. This is PQ dot. Now, just in passing, a good gauge condition can only freeze the proper gauge transformations. It cannot freeze the freedom of performing improper gauge transformations. So for that reason, if you want to impose AR equal to 0, that's forbidden, that's too strong, because if you want to impose that, well, you would have to solve a first order differential equation with respect to R for the gauge parameter necessary to bring you to that gauge, and you will not, in general, it will not fulfill the conditions that it vanishes at the two boundaries, because it would be a first order differential equation with respect to R. So in general, you cannot impose that. However, and this is something we did in the case of three-dimensional gravity, it's very easy to see that you can impose that AR vanishes at the boundary without vanishing inside in the bulk. Okay, then also you can do more, but I will not develop that here. Well, you can combine the two chiral bosons and get a standard non-chiral boson, but that's something that I will not discuss here. I want to treat gravity. And in order to treat gravity, I have to first consider the case of non-abelian Chern-Simons on an annulus, and then I will go to gravity, which corresponds, well, not only to a particular non-abelian Chern-Simons theory, one based on SL2R or SL2R cross SL2R, but also it has different boundary conditions than the one we considered for Chern-Simons. We have boundary conditions that implement this highest weight Hamiltonian reduction. So let's see how this works. First, I consider non-abelian Chern-Simons theory, and then I go to ADS gravity. So we will find qualitatively the same features, but the algebra is more intricate. But the important thing that we get conceptually the same features. So again, you can solve the zero spatial curvature condition. Now in that case, it's non-abelian, so the G would be a group element. This would be the holonomy, which on the annulus need not be 0. So I'm taking group elements that are periodic, and I put all the thing that would conflict with periodicity in the, well, that's the holonomy in this term. And K is a Lie algebra element, which you can take to be independent of R and phi, and that defines the holonomy. Okay, now when you write this, so that corresponds to what I wrote AI, DI, mu in the abelian case, you find that there is clearly a redundancy. If I multiply the group element G by a group element omega and conjugate K at the same time, this omega will drop from this expression. So I multiply by the, well, on the left. This will drop from that expression, provided omega does not depend only on time. And so there will be a gauge invariant in the description in terms of capital G. Well, actually, I should say that this really was done a long time ago in work by Moore and Seiberg and Elitzur and Rabinovici and Schwimmer. Okay. Now, using that freedom, you can bring K to some canonical form. And for instance, in the case of gravity, for the black holes, I will conjugate K to the Cartan subalgebra so that it's proportional to L0. Now, of course, you have also the Yang-Mills gauge symmetry, which will define proper gauge transformation as well when S vanishes at the boundary. But when S does not vanish at the boundary, it's what we call an improper gauge transformation. It is generated by a canonical generator with a non-vanishing charge, and so we should not take the quotient of that transformation when S is non-vanishing at the boundary. Okay, so that's a global symmetry. And actually that symmetry is generated by, again, the angular component of the vector potential taken at the boundaries. So there will be now two Kac-Moody algebras. So it will be a non-abelian Kac-Moody algebra based on the group, or the corresponding Chern-Simons group. Okay, so the current at bond boundary I will call JA and the others MA. And they form two sets of commuting Kac-Moody currents. And again, as in the U1 case, the holonomy is dynamical. So the holonomy is this, what I call capital K, will enter the action and will have to be varied in the action. But again, there is one holonomy because there are matching conditions. Now, the matching conditions take more complicated form because the group is non-abelian and the path-ordered exponential is a path-ordered exponential, so one has to be careful with that. But these matching conditions can be written. And so actually, well, I will first write them. So the path-ordered, so this would be the holonomy around that, let's say, one of the two, well, around the outer boundary. This would be the holonomy around the inner boundary. So they recall that this is a phi, this is a phi, and then they are just conjugate, and they will be conjugate by the radial Wilson line, which I have called C. So let me show the picture. So this is just the holonomy around a radial Wilson line. And the picture is here. So you see that the holonomy around here and the holonomy around here, well, I would have a minus sign or the inverse if I go that way, but they are connected. If you consider the following closed path, it's a contractible closed path, so the holonomy should be trivial, and that gives you the matching conditions that I wrote on the previous slides. Okay, so the important thing, maybe not so much the detailed expression, but just as in the abelian case, the holonomy here and the holonomy here are connected. They are not just equal as in the abelian case, but they are conjugate with the conjugation given by the radial Wilson line. And again, there is only one independent Wilson line, independent from what lives at the boundary, since I can express any radial Wilson line along the radial direction in terms of any other with different endpoints on the boundary, but then I would have also integrals over the boundaries of the vector potential phi, component phi, and that's the Kac-Moody currents. So there is only one, but that's Lie algebra valued, but there is only one Wilson line, or that's group valued. Okay, and so to get a complete description of the system, you need not only the Kac-Moody current subject to this holonomy matching condition, but also this radial Wilson line. So this is really the extension to the non-abelian context of what we saw for U1. From that point of view, the concepts are the same. Now again, also, you can check that the radial Wilson line is gauge invariant under the omega redundancy. It does not depend on which choices you make. And it will transform under the Kac-Moody symmetries as you expect it to transform. And again, if you get a non-trivial value for the radial Wilson line, it tells you that you cannot impose a gauge AR is equal to 0. Now, the brackets are more complicated this time. One can again express the action in terms of boundary actions. I will get Vesumino written terms added to the action, but it will not be in canonical form from the point of view of the Poisson bracket structure. So the brackets will be more complicated, but can be one can write the action. So to summarize, a complete set of observables in the case where you have an annulus will be given by two sets of Kac-Moody currents, the holonomy and the radial Wilson line. And so this is more than two independent copies of the set of single boundaries of observables, which are just one set of Kac-Moody current constrained by the holonomy condition that the holonomy should be trivial around the circle. Okay, so now let's go to ADS3 gravity on an annulus, and all I explained previously was a preparation of that. So why preparation? Because as we have seen, ADS3 gravity is a Chern-Simons theory based on a non-abelian group, SL2R cross SL2R. I will only focus on one copy, one SL2R, and the annulus configuration corresponds to the spatial sections of the BTZ black holes, for instance. Okay, and so a good fraction of the discussion applies, but there is one new feature, which is that the boundary conditions on the radial component of the connection are not completely free, as they were for the Chern-Simons theories that I discussed, but since we want the connection to approach the value of the connection for anti-de Sitter space-time at spatial infinity, we need to impose as boundary conditions on the connection the so-called highest weight gauge Hamiltonian reduction, which I will write again, but I explained in previous lectures. And so that will lead to a reduction of the symmetry at the boundary. Instead of, or a different symmetry at the boundary. Instead of having the SL2R Kac-Moody symmetry twice, we will get two copies of the Virasoro algebra. So actually we get twice in this case. I mean, we have SL2R cross SL2R, but then we have also two boundaries. So I don't remember if the twice here, it's for the two boundaries, but then it's also, with a single SL2R, you get it twice, but since you have two SL2Rs, you get really four Kac-Moody algebras. Virasoro algebras. Okay. And so, if you go through all the computation, as we did for the abelian case, that's very easy to be explicit. As I explained for the non-abelian case, you find that the classical state of the system, so a complete set of observables, will be given by these Virasoro generator, which are again the connected with the value at the boundary of the angular component of the connection. But now the angular component of the connection cannot be an arbitrary group element. It has to fulfill this Hamiltonian reduction condition. So there is no L0. So it's, I guess, highest weight gauge. So the coefficient of L minus is 1. But so the dynamics is really in the coefficient of L plus, and there is no L naught. And at the other boundary, you impose the lowest weight gauge. It turns out that this would correspond to, more naturally, to the black hole solution. And then I assumed when I wrote that the radial component of the vector potential was 0 at both boundaries, as I explained last time. But you can forget about that comment if you do not remember from last time. Then on top of these, so these would correspond to the Kac-Moody currents. These are pure boundary objects, well, except that there is some constraint to which I will come in a second. Then you have also the analog, well, the Wilson line that connects the two boundaries, so which will be given by an integral from the inner boundary to the outer boundary, or from one asymptotic region to the other asymptotic region of AR, path ordered. And well, again, I have written some formulas in the gauge where AR was 0 at the boundary. Not everywhere, because that would not make sense, but well, not in this definition, you don't need to know that AR vanishes at the boundary, but for some of the conditions that I'm using that explicitly, so that's why it's recalled here. Now, these variables are not completely independent, because it must be the case that the holonomy, SL2R holonomy that you compute from L of phi and from M of phi, so at the two boundaries, should match. So there is an analogous matching condition that will involve L, M, and C. And well, I wrote it, well, it's just, I just wrote it copying from Yang-Mills and using the explicit form at the boundary of the angular component of the vector potential. So 0 and I is outer boundary, inner boundary, but that's a question of terminology. Now this is a bit, if you want to eliminate that, I mean to rephrase the Chern-Simons action for gravity entirely in terms of these physical observables, in terms of the boundary data and the radial Wilson line, it's a bit a priori rather intricate, but you can simplify things if you use a Gauss decomposition of the SL2R group element. So the idea goes as follows. You write again the connection in terms of, well, as I wrote previously, so in terms of a gauge transformation and then acting on the holonomy. Okay, so, and so K is Lie algebra valued. Well, we know that for the black hole it's hyperbolic. And then the boundary values of G will determine two groups element. Well, the value of G, which I will, at the outer boundary, which I call H. The value of G at the inner boundary, which I call L. And, well, there is some gauge symmetry related to the redundancy in the parameterization of G, just as in the standard Chern-Simons theory, which is just that one. You multiply by the left H and L by omega, and you conjugate K by omega. Okay? Now, as I said, in the hyperbolic case, which is the one relevant for the black hole, you can assume that the holonomy is along L0, and the Gauss decomposition of the group element is just in terms of lower triangular matrix, the Cartan subalgebra term, and the raising operator. So you do the same for H, and for L you do the same, but because we are imposing the lowest weight gauge at the inner boundary, you take them in reverse order. It turns out to be more convenient. It's just a change of variables in a sense between this V, psi, and U and the Y prime, phi prime, X prime that you would get at this boundary by using this order. Okay, that's not very deep. It just makes things much more convenient. And then you impose the condition that that a phi should take that form, the form I wrote, that form which is here at the boundary. So if you insert that into the expression of a phi in terms of h, l, and the holonomy, you will get some conditions that you can solve actually to express completely the field y and the field x in terms of phi, and the field v and the field u in terms of psi. So in the end, you will end up only with one independent field for each boundary, and I have taken the same notation as for the chiral boson, because actually the action describing the dynamics of these fields will be exactly the chiral boson action. So if you write the action, you find, so that you start from the Chern-Simons action, you plug the expression of the field of the vector potential in terms of h, l, and the holonomy that I gave you, and in the end, and the holonomy, you assume that it's along L naught, and in the end, this is what you get. You see that you get, again, an action which looks like the action that we obtained for the U1 theory. So we have two chiral bosons, one at each boundary, and the difference between them is canonically conjugate to K0. So, well, recall that this is phi dot minus phi prime, this is psi dot plus psi prime, so we see that phi dot minus psi dot multiply K0, so phi minus psi integrated over phi is really the conjugate momentum to the holonomy, just as we saw in the case of U1. So we have, again, two chiral bosons of opposite chiralities, which have the same gauge invariance in the U1 as in the U1 case. Again, if I can make in time-independent shifts of phi and psi that correspond to the redundancy that I described earlier. And the canonically conjugate momentum to the holonomy is given by that expression, just as before. So, I mean, the formulas are just the same. So, but this is really directly related to the radial Winsel line. And so if you want to express the theory in terms of phi and psi, you can also express the Virasoro generators in terms of phi and psi, and this is what you get. If you follow because you know what a phi is, and we have an expression of L in terms of a phi, and so this is actually, that was the L in a phi that I wrote in, which appears in the highest weight gauge, and this is what you obtain as an expression. So you can either describe the system, so a complete set of observables for that system, either you can take the two Virasoro sets of generators, okay, L and M at either boundary, plus which are subject to this holonomy constraint that I mentioned, the matching condition and the radial Winston line, or you can describe them in terms of phi and psi, which have one gauge invariance at the zero mode of well, we have seen that we can shift phi and psi, the zero mode, by the same quantity. So there is one gauge invariance here, and but the other combination phi minus psi, which is invariant under that shift, so its gauge invariant is conjugate to K0, the holonomy. And these two descriptions are equivalent. But and both, in the sense that both sets provide a complete description of the observables, and actually one can even combine these. In this description, you can go beyond and compare with Liouville. That can be done, but I'm not going to discuss it here. What I want to emphasize, and that was the purpose of my talk, is that you don't get just, so what we got, and that was derived in previous lectures, if we had only one boundary, would be a single set of Virasoro generator. So now we get two sets of Virasoro generators, well, which are subject to a constraint that mixes the two. Okay, the holonomy here should be the same as the holonomy there, but then there is this extra degree of freedom which cannot be related to one boundary. I mean, it connects the two. It's a radial Wilson line. So, to conclude, since I think I am, reaching the time, I wanted to show you a very explicit and tractable example of a case where you have, in the bulk in this case, gravity theory, in this case, three-dimensional gravity, on a space which has two boundaries. And I have shown that we can very explicitly work out completely the dynamic, work out completely the set of, a complete set of observables. And these observables are single boundary observables, but in addition to these single boundary observables, there is a finite number of, let's say, global observables common to the two boundaries. The holonomy can be expressed in terms of boundary data, but then there is also its conjugate, which is a radial Wilson line, which cannot be expressed in terms of boundary data. So that means that the Hilbert space in the quantum theory of that theory would not be the tensor product of the independent tensor product of two one-boundary Hilbert spaces. And let me just finish by saying that you can extend the construction to other three-dimensional gravitational model, more sophisticated, so you can include supergravity, so you can supersymmetrize, so include spin. So it will just be a Chern-Simons theory on an appropriate supergroup containing SL2R, or you can consider higher spin gravity. In these cases, if you have sufficiently many supergravities, and if the spin is higher than 2, you will find that nonlinear terms in the algebra, asymptotic algebra, appear, but so there is a level of technical complication, but the idea is always the same, and the construction works exactly along the same conceptual lines as what I have presented. So with this, I will close. Thank you very much.